chapter 9. That is diffraction. Of things. Diffraction meaning is this. If, say, for example, if we consider cantilever beam and say here if we have the point loading, so the beam will be deformed. So here at any position, for example x, and say this is the diffraction from here to here. That's called the diffraction at the position of x. And so here the diffraction means the vertical displacement of beams. Okay, so in these chapters we're going to formulate to learn how to calculate diffraction at anywhere of the beam under different kinds of the support, under different kinds of the loading. So that is the learning goal for these chapters. If you would remember what we have learned in bending, in pure bending, because in these chapters we're going to start with basic formulation from pure bending. If you remember in pure bending, here is our beam, and the beam is under pure bending case, and this is the curvature. The curvature, basically the curvature of the beam. We denote is 1 over rho. Rho is the radius of the curvature, and if you remember that equation is m over ei. E is the Young's modulus, I is the moment of inertia of the cross section, m is a given bending. So under this equation, given the same material, the larger the m is, the beam is curved more. Okay, that means the larger the bending, the curvature is larger, vice versa. So using this equation, this one is our starting point. So for example, if we consider a beam is under the simply supported like this, and here we have the loading 4 kilonewtons, and here is 2 kilonewtons. So for this case, we can draw the shear and bending moment diagram. Because why we want to draw the shear and bending moment diagram? Because I want to get information about the bending. I want to know the distribution of the bending across the whole beam. From there, we'll be able to predict, to calculate the curvature. From there, we'll know how the beam will be curved at that positions. So here we put this one first. And to draw this one, again, if you remember, we have to first to calculate the reaction force. And for this case, this is 5, this is 1, and this is 5. So for this case, this is 1 here, and then going down here, this is -3, and going here, and this is go 2, and go to 2 here. Okay. And for the bending, that is based upon this graph. We know that the dm dx equal to b. So the slope of on the curve here will be equal to the value here. So that is like this. The slope here equal to 1. The slope here equal to -3. The slope here equal to 2. And starting from the 0, ending at 0, because for this beam, at the two ends here, there's no externally applied bending. So we know that it must be starting and end at 0. So from here, you can see right now, that is the value of the bending across the beam. And at every single point, at every single position as a position x, that follow this equation. So here I can show you schematically the deflection of the beam. So here, this is our original problem. So the deflection of the beam would be like this. At here, the bending equal to 0, so that means the curvature equal to 0. So that means here, this point, the curvature equal to 0. That means curvature equal to 0. That means that is flat. Okay. And then from here, is that right? M over sigma over EI. Then from here, the bending increasing, so the curvature will be something like this. So here, right now, I'm drawing is the shape of the beam will be something like this. Okay, and then to this point, the bending equal to 0. The magnitude of bending equal to 0, so somehow to this point here, the beam will become to, again, the curve here at this point, that is 0. And then come up to here. So here the beam won't, that is supported at here, so that won't move up and down, so we come to here, something like this.
Is it the opposite of, so is the magnitude of the beam, like the way it's bending, the opposite of what it is in the moment diagram? Like how?
Yes. When bending, here is our defined positive bending. This is our for sign convention is positive bending. So when bending is like this, then it will curve up like this. So in this portion, this is positive bending. So that means corresponding in this portion, that is curved like this one, curve up. Okay. So here I don't know whether this point will be 0, the deflection at this point will be 0 or not. So I'm not sure. Okay, so here I'm kind of writing, how about this, to make things, so let me make it in general just like this. I don't know. I don't know the deflection at this end will be 0 or not. Who knows at this moment. So but this way will give us kind of schematic showing to see that is the kind of the shape of the deflection of this beam under this kind of loading. Okay. And so for this case, we asking, do we have the more precise or accurate method to really tell us what is the deflection for this case? For example, here, this is a position x here, so that is a deflection y of x. We want to know what exactly is the description of this function. And that is the learning goal of these chapters. We want to derive the equations and for writing up this one.
Can you explain why that beam is curving up? I don't really see. Okay,
where? This one here?
No,
here,
you were
this
talking
portion.
about it earlier. Yeah.
Yes. So again, for our sign convention, the n is positive when the n applied like this. Okay, so once we have the beam, and the beam is under, for example, the positive bending, then the beam will be curved like this one. So the curve up corresponding is the positive bending.
Okay. Yeah.
Okay. So now again, this is the target, this is objective we're going to run in these chapters. And then for the remaining today and Friday, the 2 lecture hours, we're going to exercise. The first one today, I'm going to give you the formulations for deriving this function, and then Friday we're going to do quite a bit of exercise examples, and then hopefully Monday next week we can finish these chapters by introducing the applications of the techniques for this case. So now keep this in mind, and we come to our formulations. Everything starting from here. The formulation is this. Given the magnitude of the bending, and the bending will be the function of the positions. Okay, like this example, you can see the magnitude of bending basically changing, is varying over the place from another. And we're given the Young's modulus, and we're given the moment of the natural eye. So which means the geometry, the dimensions of the beam is given, and the material property is given, and n should be derived from the given loading condition like this. So we're going to calculate the y of x diffraction. The solution is simply like this. We start from here. Starting from the chapter 4, the m over ei, and from this case, m is a function of x. So this is the curvature. Curvature will be also the function of x. Okay, we're starting from here, from this moment. And what is the curvature? If you would remember in your calculus, I think everyone should have learned the curvature before. But let me do this very quickly. And what is curvature? So here is the simple, very, very quick review. So for example, if we consider two-dimensional curve, for example like this, and let me say this is the y of x. Okay, this is a curve. The y of x is a 2D curve. Okay, so at any point, we take the tangent. So this is the tangent, T-A-N-G-E-N-T, to y of x at point A. Okay, so that is the definition like this. So tangent, that means that's a straight line. And for example, for this tangent, say that tangent has an orientation, say we can measure the angle theta. Okay, so here that is, again, starting from the fundamental definition. So we, at every point, we can make, for example, at this point, B, we can make another tangent at the point B. And at the point B, you can see very clearly the tangent at the point B has the same. For example, here the tangent will be like this. So that means at point B, the tangent has less angle theta than compared to A. And say at point C here, the tangent is even more steeper. So that means you can see the orientation of the tangent through this curve is changing over the course. Right? And the measurement of the change in the orientation basically is quantified by curvature. Okay, the curvature definition is just that simple. So let me say the curvature is kappa of x. Okay, the kappa. So usually the kappa of x is defined by d theta ds. The s is, for example, here we measured the s is the s is the length along the curve. Okay, so we measured is the change of the orientation of the tangent along the traveling of the curve. So that means we take the length for how far we travel from a reference point to the next one. So we take the ds. So again, literally, the curvature simply described is the change of the theta along the curve. And here, the ds in terms of our corner systems is dx squared plus dy squared. So for any small movement, we take the dx and dy. So again, those are the definitions here. And what is d theta? So right now we have ds be formulated like this, and what is the d theta? And right now my goal is I want to express the d theta in terms of something like the x and y. Okay, in the way we can do the calculus. So what is theta? So here is a way. You can see the theta here at the point A representing is a tangent to the curve. So that means tangent theta equal to dy dx. Again, dy dx, that's the function of the x. So for example, say at point A, we take the tangent, which means the dy dx, that representing is the derivative, and we give that one. And that representing tangent by theta, that gives us is the orientation. And again, that is from the fundamental calculus. So therefore, here we can see the theta equal to arctangent. And say here, let me save my time. Say let me define this is a y prime. Okay, I use the prime. So here is the derivative of y prime x here. So therefore, d theta will be equal to d, and here's a little bit writing here. Okay, so here for simply for easy kind of the scene, I drop the of the x and to make that clear. So in this way, this one again, the derivative of this one we can put into like this. Where's my formulations here? So maybe we just save it at this moment. So therefore, from here, the kappa of x, we plug in everything here. So that will be d arctangent y prime, and ds will be equal to this one, dx squared plus dy squared. Okay, and then for this case, let me rewrite the things. Let me rewrite the denominators into this form: 1 plus dy dx squared and then dx. So simply is this. For each term, I divide it by dx squared. So basically denominator equal to this one, and then just keep writing the numerator the same thing. So from here you can see this denominator here is 1 plus dy dx is a y prime. So let me change the symbol again. And here is d tangent minus arctangent y prime dx. Okay, become like this one. So right now we simply is to calculate the derivative of an arctangent respect to x. And for this case, we can look up the tables from the calculus tables. So basically here, let me rewrite here one more time. So this is 1 plus y prime squared. And this one, if we implement this one carefully, that one actually is equal to, let me see. That one is equal to dy dx, theta dx. This one basically is equal to d squared y dx squared and 1 plus dy dx squared. Okay, so again, this one is this one. It's nothing special. I simply look up the tables. So again, let me rewrite these things. And right now, the denominator is here. In this form, I introduce y prime equal to dy dx, and y double prime equal to d squared y dx squared. So that means the denominator will be equal to y double prime. Numerator will be y double prime. Denominator will become y plus y prime square and 3/2. Right now I combine the both into here. So this is the curvature. So this is our kappa x. So this is our curvature. So right now we have a curvature. We've introduced back to our the equations. So that means to solve for the diffractions, so that means y double prime 1 plus y prime square 3/2 is equal to m of x over ei. If you will be able to solve for this equation for y, then you got the problem down. And look at this equation carefully. This is a second derivative of the y function. And what is y? What is y? Y representing is a diffraction of the beam, right? We introduce here, and in our example here. So in this case, this is the diffractions, and this is our y, right? Remember, we're looking for the y representing in our beam diffraction is the diffraction of the beam. So this is the second derivative, this is the first derivative. So basically this is the second order nonlinear differential equations, the ordinary or the INARY differential equations. If we will be able to solve for the second order ODE, then we solve for the problems. So mathematically, we have to deal with the differential equations. And here, I think the prerequisite will not be right, and everyone must have taken the Math 302. Calculus.
Yeah.
And I think most of us have taken ODE.
I think the prerequisite was only
Only Calc 2.
Yeah.
Only calculus. Oh my goodness, I need to go to okay. Does anyone don't know how to solve for differential equations? Okay, so no one responded. I assume everyone should know. Okay.
I know that there's going to be a lot of difficulty.
Difficulties. Okay. So that is not my job. I'm not teaching differential equations. Okay. I try to clarify the job duties. But don't worry. I will give you whatever the tools we needed for this class only. So that means you should have enough tools from me to solve the equation for this class only. Okay. So for this equation, you can see that one, basically, I can tell even for me, I will spend time to solve for these nonlinear equations because I need to look up the calculation table, the calculus tables for this one. And this one is very hard to solve. And most of the time, we have to go to the numerical simulation, the coding, do the programming to numerically calculate for the y function.